So, hello, my name is Don Paul Stevens. I'm founder and CEO of AirMettle, and I'm here today to talk about a computational storage service. It's an analytical data platform that has the ability to do intelligent analytics offloads. So, let's take a look at computational storage. Look at the devices. And you've probably heard a lot about computational storage. The concept has been around for quite literally decades, and brings back pretty fond memories of graduate school back in the 90s. So, like Eric Rydell, I just realized it was quite a shock. He passed away this last year. So I remember him giving lectures about the work he was working on in his PhD about active disks, and he graduated in '99. So, but really want to step back and say, this concept of computational storage, why hasn't it really made a significant impact? And what can we do to really put it to work and make a really dramatic improvement in how we build and manage storage systems and deliver analytics to clients? So let's take a look back through the years. Computational storage. So when I was first introduced to the concept, in the late 90s, it was research at Carnegie Mellon and IBM, and it was research, so you weren't really expecting it to be in the product. And of course, thud, hits a wall. And then you say, then there was a concept of processing and memory, which Micron and Samsung really came up with the concept. And but the problem was putting a processor in the memory devices was kind of prohibitively expensive and really didn't get any commercial interest. So thud. And then go forward, and then there was some concept of putting FPGAs into the SSDs. And so a number of companies like ScaleFlux and Samsung with their smart SSD and NGD experimented with ways of what if we put an FPGA there, and what do we see what people might do with it? It was really complex, it was expensive, and it was kind of are we going to put a computer in a drive? And what is it going to do much more in a standards compliant way besides just internally compressing something? So if you got to NVMe, that made it a little bit easier to consume, but it turned out that it seemed that the people that were able to keep these commercially successful were ones that were effectively customizing a pseudo embedded system with some of their customers, particularly in the case of ScaleFlux, is from what we see from some of the public statements. But again, I've only seen some stuff externally. And now we're looking at the concept of using software-defined systems. And there'll be another talk later today from Kioxia about some stuff that they're working on for doing some RAID protection inside the system. And we've been talking to Phison for a while. So it's really refocusing and looking at the use cases and seeing if you could support what the software is doing on a particular host. So we really think of it's kind of like looking from a device-centric approach of computational storage to now it's somewhat of a more host-centric approach, but there's still limits to what you're able to achieve if it's device level or host-centric whenever the storage in these modern systems are really stored across a very vast service that spans literally hundreds to thousands of devices. So if we look at the host level approach, it has applications, but clearly there's limitations. And so what might these be? Well, if you look at how storage protects data, way back concept of RAID, erasure coding, it's basically moving lots of data, and you have a very simple comparison function. So it's trying to protect your data. And these are tried and true methods, been used for decades. And these are really brought up in the point of time where gates were horrifically expensive. It's not that the wires were free. I mean, you literally had people wire wrapping things. It's that the gates were so incredibly expensive to manufacture that it was dirt cheap to have people wire wrapping things. You literally used to do this. So now if you're going to protect data, so it's okay, basics have an XOR code. Why don't we take a look at it? If you look at a set of data and you put them into cut nice, fixed, uniform boundaries, ka-chunk, 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 Well, it seems like this is a straightforward process. We've done this for decades. Works for hard drives and SSDs. Kioxia, as I said, will be giving a talk about this on their computational storage hook later in the day. But so what's the problem? So you can protect your data in case anything is lost. Well, let's take a look at this table. And if you take that data in the table and put fixed set of bytes down into the drives, yuck. What happened? Well, we basically shredded the data. Some of the metadata is in one place, some of the data is in others. You're cutting key records and entries off. You can't actually analyze anything anywhere. But it's nice uniform fixed size. But that's not the problem today. The problem is how do we actually analyze and get insights out of the data? It's not just you store it, you retrieve it, send it somewhere. The networking itself within the storage layer, the networking is increasingly being the bottleneck. You have insane amounts of compute in almost everything you pick up these days. There's more compute power on my wrist doing just about nothing but then the entire planet had to put a man on the moon. I mean, think about that. Processing, if you can tap it, is effectively free. It's moving the stuff around that's getting so expensive. And that's probably why big data just seems to be so slow. So how do we make big data not be slow? How do we get insights more quickly? So we look at this and said, well, what if we take a different approach? What if we can look at this and say, what's a systems level approach to looking at this problem? How do we enable much faster and more efficient distributed analytical processing? Because your data, whether you like it or not, or really recognize it or not, is actually stored in a massively distributed manner across a vast fleet. So do this. We took out Occam's razor to this Gordian's knot of analytics and said, how do we make an actual computational storage service across a vast number of systems? So if you think about that issue where we showed a very trivial table and it doesn't actually partition. Well, what we do in our system is that whenever you ingest data, there's a lot of common data formats that are incredibly pervasive. And you would suspect that because you can have different applications open data files that are the same data type, we're actually taking advantage of that within our system, that whenever data's been written into our system or put, then we will actually look at the boundaries and effectively bring out a super precise X-Acto knife, you can think of it. And we effectively precisely cut the data and effectively wrap it in a very lightweight envelope so that we're able to keep processable components of records together whenever they land on back-end storage. And so this concept is we keep the original object metadata, but we will store just a tiny bit of internal metadata on each one of the cuts. This is very much not to scale. I mean, the typical overhead that we add to enable fully distributed parallel in-place analytics is typically 0.1%. It is completely dwarfed by the overhead of data protection. Now, but you probably noticed that, well, the issue I showed earlier was that when they were fixed nice sizes, they didn't align perfectly. So yes, the data elements that are stored on the back-end storage devices are not actually fixed size. But we think that's not really a really huge problem, because whenever we take the data elements that are now potentially variable size, there's some variance, but we simply correct that in the erasure code. The erasure code algorithm doesn't become that much more complex. It's a little bit trickier, but it's trivial in the grand scheme of things. So if we look at this and say, well, what are you actually able to do if you're able to divide data and do processing on those subcomponents in parallel? So we look at a number of applications of classic tabular data, whether it's CSV, JSON, Parquet. So these are widely used in analyzing historical data, looking at current events, so security, information, event management type applications. You have a lot of data which is collected in JSON, like could be things like the reports that Dan was just talking about, or it could be like just about anything. It's amazing how much stuff gets collected in JSON today. And you're looking at statistics, you're monitoring things, you're trying to analyze the content. So how do you, what can you do with this? Well, you have a basic select API. So Amazon had introduced a select API directly off their object store. It wasn't actually that fast. Our system is quite literally 100 times faster. The reason it's 100 times faster is we divide the data, and the components that it's stored on can actually be processed and filtered while it's stored in a massively parallel manner. And a lot of these basic SIEM type use cases, like you need to parse and go through all the data, but the amount of content that you actually need to return is typically 3 to 4 or more orders of magnitude downscaled. Like literally there's orders of magnitude of more content like that is in the storage than is actually needed to return very basic answers. You might need the statistic, you might need like the average, you might want to know how many elements are between this range and that range, meeting a certain criteria. And the bottleneck again is the networking to moving all the data from your storage layer to your compute tier. If we can actually process the data and return the answer, it's going to get the answer to the client faster than you could even fetch the content. Now, okay, so this is 100 times faster. So I know with Silicon Valley, everybody likes talking about factors of 10, and there's a factor of 100. Well, like, is that okay? Well, there's 100x, but of course, the question is, it's 100x of what? So like, how much of the more complex problem is this 100x? So if you look at something like Starsky benchmark, then the simple scan, filter, aggregate will many times turn out to be something between 2/3 to 80% of the runtime. And if you look at your classic Amdahl's law, if you take the big problem, you take like the 80% problem and you squish it by a factor of 100, you're still left with the remaining 20%. So unsurprisingly, if you look at this, we run this on a more complex problem and using, say, Apache Spark that's going to interface to our system, since we're able to do the scan, filter, aggregate within the storage layer, what you get is a net acceleration of a more complex problem by a factor of 5. It basically varies by how much of this portion of the problem we're able to do like in the storage layer. But this is effectively just by swapping out the storage and having the right API to basically say, I don't want to retrieve the whole object, I just want to process the object and give you the answer. So that simple change alone can get you a factor of 5. And the higher level tools, they're the same. So what kind of analysis can we do with this? So we looked at this, and there's a, like if you look at the classic SIEM type use cases, they have to do a number of things like collecting samples, identify certain flags, group things potentially by minute or by some other metric, and then you're returning a number of statistics. So you're basically like a more complex set of processing, something potentially like that. So, and this is the nature of the kind of SQL that we can support like in our system in a massively parallel manner. So it's more complex than S3 Select, but it's still fairly basic. But these are the common set of reporting queries that you would see in a typical SIEM type use case. And of course, we return the data not in human readable text like the S3 Select API does, but we can also return it in arrow so that it's directly processable by the tools whenever it lands. So there's adding basic data organization, data characterization, like basic things like group by, standard deviation. This gives you powerful tools. You can actually do quite a bit of basic processing. And one of the things you probably picked up on is that a vast majority of big data you collect today, you have to collect the content to find out what's in it. And so you'll collect a huge amount of content, and you're trying to say, like, what is normal? What is abnormal? And then you got to find, like, what is the range of the piece of the abnormal bits that you're actually interested in drilling into. So you're going to have to collect a lot of data. You're probably going to keep it stored around for a long time, but you want to be able to get the relevant insights and then compare that data to how it changes over time. Now, so we've been working on this for a while, and then obviously one of the key people who's been pushing the industry for like enabling like computational storage because it can solve their problem is a team at Los Alamos, and they asked us, well, if you can enable distributed processing, then can you go back to this problem of can you actually put something in the device? And what's the right layer to push something into a device so you can get another scale up? Because we solved this on a scale out, but there's been a lot of industry focus, again, for like 25 years, on like how do you scale up in the device? And so what's the right way, in our view, of doing device level processing to accelerate this? So in effect, if you're looking at the SSD, how do you go from this concept that's been around for 25 years and make it something that is able to really look and attack your problem head on and give you actionable answers much more quickly in a hardware accelerated manner? So what kind of use cases do we want to look at, and for whom? What are the real drivers for this? So a lot of massive amounts of data, say SIEM type data, security information, event management, network operations data. So there's, like, these are representative. These aren't our current customers, but these are like kind of companies illustrative that have these big problems at scale. Weather, climate data. So who's interested in weather data? It's not just weather forecasting, but weather forecasting is actually very important for doing things like power pricing and natural gas pricing, because temperature really drives power demand for HVAC. And if you find things like cloud cover, then this is going to determine the kind of solar output you can have. Wind provides like what you can get out of the turbines. So there's a lot of large financial markets that want to take a lot of this data and optimize it and analyze it so they can trade on it, they can get insurance products priced from it. Semiconductor process. So there's a lot of companies who make chips, then make sure that things are produced uniformly or like find variations that shouldn't be there, real-time analytics. So there's a wide variety of use cases that people are collecting these mass amounts of effectively array-based data, generally keep them in blobs, and in some cases these are like write once, read maybe, or if you find that it's something of interest, then you read it a massive amount of time. So what kind of operations are really going to be applicable to the kind of analytics that we've been focused on? We really see them as like a select or a multidimensional select type query. But then you say like, well, like, don't talk in the abstract, like to push something in the device, specifically what kind of data type, data formats are you looking at? Like, well, like common ones that people see are like Parquet and Iceberg. So these like columnar array-based data formats, or if it's weather data, it's NetCDF, HDF5. Like you have arrays of data to give you addressing and to where the other arrays are. So these are starting to look rather complex. Like, yeah, they're public data formats, but it gets really hard if you're going to say like, well, like you have some open source code, like to run it. It's like, these can get very complex. If you put too much complexity into the drive, you're effectively turning it into another computer with all the various overheads that are involved. So if you ask a question of, do you want to or can you cram like a modern processor and operating system into what effectively amounts to a hard real-time embedded controller? Like branches, branch prediction units, memory management, security issues on those can get to be hard problems. these complex data types, which might change. That gets a bit even worse. And trying to navigate all this, it starts to look like it's almost seemingly unbounded complexity. And and we stopped and said, well, Henry Youngman's classic. It's like the patient says, "Doctor, it hurts when I do that." And of course, the doctor always says, well, don't do that. That's like not a good idea. So what do we think is an alternative way of handling this? So we looked at this and identified that you could have a different paradigm. So we're looking at having a technique where you can effectively look at the data and say, like, if you have the right to read the data, can you do a very basic operation on the content? And the kind of basic operation we see is the notion of being able to check something and then like use that as well to fetch. So a very simplistic check fetch API. So understand people have come up with very complex approaches for what you might want to delegate to storage for a long time. But when we're looking at this, we think it's better to pick something which is simple, basic, and can be proven to work at scale. There's plenty of time to add complexity. What we need to do is be able to say, how can we find a base common layer that can be applied efficiently at scale, and ideally have the ability that can actually run at line rate? Because like cost is important. And I think some of the problems of the historical approaches for computational storage is they've turned out to be too complex to use, too complex to manage, very expensive to manufacture, separate supply chains. When you compound this, it basically ends up that it's fascinating for printing PhDs, but it turns out not to be very effective for making a big market impact. And we want to have something that makes a big market impact. So if you say like, well, check fetch just seems relatively simple, so like what kind of scale could you apply for this? Well, if it's broken down to the individual elements, it's obnoxiously parallelizable. So if you take something like, say, 20 gigabyte per second internal bandwidth of like a modern SSD, but your base LBA size you're accessing off the flash is 4 kilobytes. Well, how fast do you need something to run if it's processing 4 kilobytes at a time? Your internal controller could run this at 5 megahertz. Megahertz. Yes, you can have something that can run incredibly slowly and keeps the power down and avoids the need to move the data even from the drive to the host. So you get a dramatic reduction in the operating frequency required and the amount of content that needs to move. And we're looking at things where you literally are taking a bit. Like, because if you check it, the answer is T or nil, yes or no. Do we match it or not? So how could you apply this? So we look at, say, some Parquet data, and you have a very simple common query. So it's like, take a table and you want to select customer, order, Parquet, revenue. So like there's a lot of fields. But you're looking for things in particular where like there's a selection that you want something between the quantity between, let's say, 11 to 20, and the order date is less than it's within a range. So how can you do this on Parquet data like stored in a remote system? So if you have the drive, you say like, well, this is easy, it's Parquet, here's this library. You simply have to run it in a Linux environment, and it's like, no, that's too complex. Well, if you know where the data is and what the boundaries of the content within the objects are, then the host can maintain the control of where you go in the object, what you have to do. So the host, our view is that the host needs to maintain control over what is done on the content. We can tell you where, and there's a simple operation. The only requirement is that it's array-based processing. You want to do continuous processing over an array. So with a check-fetch approach, when we're pushing the basic processing in, we had to read the footer. We had to find out where the boundaries are. Where's the starting position of that array? But then, since all the elements in the array are one after another, it's a completely sequential operation, check every individual field, then you can check each one of these cases as basically a delegated check. Check this field from this point to that point, give me a bit field in return. And then you check one, then you check the other field. Now, if you have like a CMB, controller memory buffer, then you could actually take these intermediate bit fields and even just write them into a local memory on the device itself. Therefore, avoiding the need to even move content for the intermediate processing back to the host. And you can compare on one and compare on the other, and then you have simple operations. Quite literally, like in this select field, it's an AND. You could do simple arithmetic operations between bit fields and do those on the drive as well. And that enables you to take what looks like fairly complex SQL, and you can actually do those operations on the drive itself. And then whenever you get a resulting bit field, then that field, you can then use it to fetch data off of other separate arrays. And it's just, since it's a bit field, the size might change on which fields you're returning. Is it a 1 byte character? Is it 4 bytes, 8 bytes? It doesn't matter. You don't actually care what the elements mean. The only things you need to know is that if they're fixed size elements, you can use the same basic handshake to then retrieve data elements. And then what you get back is nice, packed, like in memory. So quite literally, you're taking that, and then instead of getting this whole table, with a few operations, you're able to get it to a very tiny subpiece. You can literally cut the data coming to the host from a drive which is connected to that host by 2 orders of magnitude. And you might wonder, geez, this seems like really complex. And so, can you support this in any device? Yes. So Faizan, who have talked to some others, so it's completely practical that you can actually implement these sort of check fetch APIs for enabling delegated analytical subprocessing to the drives themselves. This can be done in firmware or hardware on existing commercial shipping drives. So we're looking at collaborating with Faizan and or others, potentially bring some of these capabilities to market for systems like ours going forward. So we should give some acknowledgments that some of our work has been supported with some government support under grants from both the National Science Foundation for basic core scale-out analytics, National Oceanic and Atmospheric Administration, the work that we're enabling for processing like climate data models in CDF, and the U.S. Department of Energy for some work we're enabling for doing parallel AI inference on like multimedia data sets. So see, that's a quick overview of our computational storage service on our analytical data platform. So if anybody has any questions? So, a lot of slides. Hopefully it was entertaining. Any questions?
I have a question.
Sure.
Have you considered, you were specifically talking about CMB for doing these data manipulations. Have you thought about using some of the NVMe extensions that have been standardized around subsystem local memory and computational programs?
Okay, so you're asking if we've thought about, besides CMB, if there were other like hooks that are standardized on NVMe. So we're talking to a couple of different device vendors about this. So we're a software-defined storage vendor. So we don't actually make hardware. I'm kind of I try to make been there, done that, lost a T-shirt. We want to work with other companies that are enabling that. So we're talking to some partners that, like, how would it best be to implement our architecture with their systems. So we're like CMB is an obvious one. The other thing is that the check fetch nature of it is both that we're providing some data to the drive for what needs to be done, and we're retrieving data, whether it's coming back to us directly or even if it's being written into an internal memory such as a CMB. So there's a fuse operator that makes it more straightforward in NVMe to be able to have two commands that kind of go back to back. We've been told that some operating systems aren't really friendly to fuse. So we're looking at the practical ways that this can effectively be implemented and used through a standard Linux stack. Did that answer your question?
It helps, thanks.
Okay. Yeah.
So you're using the equivalent of the SQL queries on the host, but pushing effectively that query to the drive?
Oh, no. Go ahead.
So my question is, so in order to build that mapping,
yes,
are you also providing the interface to your customers to say, I need to convert this query for use on the computational storage?
Oh, that's entirely hidden from the client. So he was asking do we provide a mapping so that the client is seeing how we've unrolled this. So we're a software defined storage system. So it's connecting to us, and it might issue an S3 select API or an Arrow, a select API through Arrow, an ADBC connector, but we have the data stored in a massively parallel manner across a large number of storage nodes. So we're the software that's running on the host that's connected to potentially the drive. The handshake of what our host sees. So our host is one of many components in the fleet that implements the service. So our node will see that we have data that happens to be in Parquet, and so when we see that there's Parquet data that we have to implement to select, we can potentially retrieve the data from the footer, and the host will process that to figure out where are the actual boundaries where each one of these array components begin and end. And the only thing that's pushed to the drive, we want to push to drive, is the range checks or the fetch operations. So what the drive sees is effectively be a check this, say that we assert that this is an int 32 or it's a float 64, and we're doing a range check or something. So we have a very basic, this is a check operator that we want to run. It starts here, runs for this long, and we're getting a bit field back. Whether the bit field is coming back in a CMB, or the bit field comes directly back to the host. We're looking at the most practical way to implement that, but our view is you want a simple handshake, but all the drive needs to do is run these very basic check or fetch operations. It doesn't know that it's doing SQL, and if you're doing something you want to get the average precipitation or whatever, on a range of data in an netcdf4 file, you can still break that into a number of simple components, which amounts to range checks to get values. So we want to keep anything which is dealing with the more complex nature of how the data structures are built, how do you interpret them, those are done on the host. We want to delegate effectively the data path portion to run on the drive, because that's something that is very simple to delegate cleanly. That answer your question?
Yep.
Okay, thank you. Yes, sir.
Are you using a standard NVMe approach to do the communication back and forth with the CMB, then to actually do the analysis, push it into the CMB, and then have it be accessed?
So are we doing a standard NVMe approach? We're talking to some partners about the right way to implement this, and whether it's on standard NVMe commands or if it's potentially vendor specific commands. So that that's still in the to be determined camp. But we would like this to be as standardizable as possible. The real objective is that this should be able to be implemented completely in firmware. So we will aspire for this to effectively be it's just a change in firmware on the drive, and the drive can just delegate and just do this in place, because it is It's actually alarming if you go into the numbers, like you actually have more scan bandwidth like in the SSDs themselves than you do, like if it's fully populated, than you do in a server's DRAM bandwidth, which seems nuts. But if you look at like an SSD has like 14 to 20 gigabytes per second like read from each device within Gen 5, and that like you can have servers that have like 48 drives. Like your DRAM bandwidth is like it's a bus. It's unidirectional. It's like 300 something after you take a RAID. Like bus turnaround overheads. You don't need many SSDs to be able to literally have the ability to scan in the drives faster than you can in DRAM. It's mind-boggling. But like that's the path we want to go to. Okay.
Yeah, I guess a follow-up to that, related to the data transfer approach. I'm coming from a biased point of view. That's my talk later. But are you using like PDB-DNA to do the communication then, or how are you accessing the drive, getting the data to write from the drive onto the CMP internally?
So how are we managing writing the data? So again, we're not a device vendor. So we've solved this as a scale out on like the software layer, and we've been looking at how can we push that capability into the drive. We're talking to a couple of SSD manufacturers about like what is the right way of doing the handshake, but like that's like we're going to be driven more by like what is the particular trade-offs that the partners we're talking to could actually implement. And I don't want to be too fussy about like it must be done particularly this way. We just like we want to get these basic operators, but the operators that I showed you, like they're very simple, but if you can chain them by the host control, it's very powerful. Okay, anybody else? So, not then. Guess you could like thanks everybody, and like please take a moment to rate the session. So hopefully it was useful and entertaining. Thanks everybody.